Hello everyone, welcome to Lecture 21. So our theme today is inner products. We're just starting the short chapter 4 of the lecture notes, which is about the concept of an inner product, which is a device on a real vector space, which really resembles the ordinary scalar product. So just before we launch into what that means, let's recall a few of the details about the ordinary scalar product. Okay, so the ordinary scalar product on R2 is the familiar one. If we have a pair of vectors AB and XY in R2, then their scalar product, which is indicated by a dot, is just the product AX plus BY. So it's that algebraic operation in terms of the entries of the two vectors. Of course, if we want to write out two vectors, that's more like coordinates of points in R2. We can do it that way too, and the same applies. And we know that this ordinary scalar product captures certain important information about the vectors involved. So if we have a pair of vectors U and V, then we know, for example, so if U, for example, is a vector whose coordinates are, let's say, A1, B1. So the typical picture of that in R2 is that we've got a point whose coordinates are A1, B1. So here's A1, here's B1. And U is represented as a vector by the line segment directed from the origin to that point with those coordinates. And we can observe, for example, that if we consider U to be this line segment, then we can talk about its length because it has a length as a line segment. And the length of U has the property from the theorem of Pythagoras that its square is equal to A1 squared plus B1 squared, the sum of the squares of the two coordinates, just from the theorem of Pythagoras. And that tells us that the length of U is equal to the square root of A1 squared plus B1 squared, which is equal to the square root of the scalar product of U with itself. Okay, so from that we can see that we can use the concept of the scalar product to define the idea of the length or magnitude of a vector in R2 in a way that's consistent with our concept of or understanding of the idea of length in the Euclidean plane, where we can talk about the distance between 2 points. So the length of a vector with coordinates A1, B1, then we can say is the distance from the origin to the point whose coordinates are A1, B1, and it also can be realized as the square root of the scalar product, the ordinary scalar product of U with itself. We also know that if we take a pair of vectors, U and V, in R2, and represent them as directed line segments from the origin, then the scalar product of the two of them captures information about the lengths of the two vectors in question and the angle between them. So if we call that angle theta between U and V. So we also have the fact that the inner product of U and V, the scalar product of U and V, is equal to the length of U, defined in this way, according to that formula, multiplied by the length of V, multiplied by the cosine of the angle theta between U and V, where they are located in the plane with their initial points both at the origin. And that means that the scalar product, which is a very simple thing to compute in algebraic terms, here's the definition up here. It's just this sum of products of coordinates in corresponding positions, but it carries information about the lengths of the two vectors and the cosine of the angle between them. So in particular, we can also point out that at least if U and V are both not non-zero vectors, then the scalar product of U and V is equal to 0 if and only if the cosine of the angle between them is equal to 0, because if U and V are non-zero vectors, then neither of their lengths will be equal to the number 0. And this happens if and only if the angle between the two vectors is pi over 2 or 90 degrees, which means that the two vectors are orthogonal to each other. So U is orthogonal to V. So we would say this by saying U is perpendicular to V in the sense of sort of ordinary angles, but more generally, U is orthogonal to V. So the ordinary scalar product in R2, basically it kind of encodes a lot of the geometry of vectors in R2. It gives us information about the lengths of vectors and about the angles between them and about this key concept of orthogonality, two vectors being orthogonal to each other. That is captured by their scalar product being 0, as long as we're talking about two non-zero vectors, of course. The 0 vector whose coordinates are 0, 0 is orthogonal to everything, but doesn't really make angles with other vectors because it has 0 length. Okay, so that's a quick recap on the ordinary scalar product in R2. Okay, so in the case of R2, it's envisaged as the ordinary Euclidean or Cartesian plane, so it sort of comes pre-equipped with a certain amount of geometry. We can talk about distance between points, angles between line segments, and so on. When we're talking about R2, we can already have a notion of its geometric structure. And we can observe, after defining the scalar product in R2, that actually encodes quite a lot of the geometry in terms of lengths of line segments and in terms of angles between vectors and orthogonality. So one could take a different viewpoint. If you were working in a vector space that didn't come already sort of pre-equipped with geometric structure that we could sort of visualize or even sort of physically engage with, but if we had something to do the job of the scalar product, then we could use that something to define concepts of distance and length and orthogonality and maybe even angles between vectors by analogy with how it works in R2 or R3 or in the familiar Euclidean spaces. And that is exactly the idea of inner products. So an inner product is a abstractly defined function related to a vector space. But in order to get a kind of concrete handle on it, just keep in mind the ordinary scalar product on R2 is enough to really sort of capture the thinking behind this definition. Okay, so an inner product on a vector space V is a function that takes pairs of vectors in V to R. Okay, so this V cross V, this is the Cartesian product of V with itself. Its elements are the ordered pairs of elements of V. So the inner product takes a pair of elements of the vector space V. That's why it's called a product, because it takes two things and puts them together. It puts them together and assigns to that pair a real number. Okay, so the values of the inner product are real numbers, just like the values of the scalar product are real numbers. They're not vectors, they're scalars. So an inner product is a function that takes a pair of vectors to a scalar, just like the ordinary dot product or scalar product does in R2. And we insist that it just shouldn't be just any old function, that it should have some properties, as usual, that respect the vector space structure. So we're going to write this notation x comma y, brackets around it, for the inner product of x with y. This is a kind of confusing notation because we use the exact same notation for the subspace spanned by x and y, which is rather inconvenient and certainly leads to the risk of misinterpretation. But this is nevertheless widely used. So this angle bracket xy means the inner product of xy. It itself is a real number. And we want the function that takes pairs of vectors to real numbers to satisfy the following properties. First of all, we want it to have the property of symmetry. And that means that for any pair of vectors, the inner product of x with y should be the same as the inner product of y with x. It doesn't matter in what order we put them. Okay, and that is certainly true in the case of the ordinary scalar product in R2, so it satisfies that property. Okay, the second property that we require is this bilinear property, that basically, if we take a linear combination of vectors in V, and we want to calculate its inner product with some other vector in V, that we should be able to sort of distribute the inner product over this sum of scalar multiples. So in other words, if we want to take the inner product of ax plus by with z, where x and y are elements of the vector space and a and b are scalars, then that should be the same as taking ax with z and by with z and adding those two over in the real numbers, and also that we should be able to pull out the scalars. So basically, this expression should be equal to a times the inner product of x with z. So remember, these two are objects of the same type. Now xz is a real number, and so is a. So this expression should be equal to a inner product of x with z plus b inner product of y with z, and same on the other side. Okay, and certainly again, we can confirm that the ordinary scalar product in R2 has this property of bilinearity. The third property that we require, I refer to it as non-negativity just as a kind of shorthand for it, but what it's saying is that if we take the inner product of any vector with itself, we should get a non-negative real number. So we should never get a negative number by taking the inner product of any vector with itself. And the only time that we should get zero should be if x is actually the zero vector itself. Okay, so this is saying that the inner product of any vector with itself should never be negative. In other words, it should be a number that has a square root. And also, the inner product should generally be positive unless the vector is the zero vector. So this is kind of related to the idea of using this inner product of a vector with itself to somehow capture a notion of length of that vector, which of course should not be a negative number if it resembles in some sense a length or distance function. This is certainly true in the case of the ordinary scalar product, because the ordinary scalar product of any vector in Rn or R2 or R3, Rn generally with itself, is just the sum of the squares of the entries. And that's never going to be negative because the squares of the entries can never be negative, and it's only going to be 0 if the entries themselves are all actually equal to 0. So if we're dealing with the 0 vector. So these 3 properties, okay, maybe it's not completely obvious why we would single them out and choose them to be the properties that we really want to be satisfied, but we can at least confirm that they are satisfied in the case of the ordinary scalar product on R2. Okay, so the kind of go-to example of an inner product for us is going to be the ordinary scalar product. And that would be the main example that we use in our discussions. So, and it's the most familiar one, certainly, and kind of the most obvious one, but it's certainly far from being the only one. And there are other examples of inner products that people do use all the time. And the first example I want to mention in that regard is something that might already be familiar to you, depending on what else you're doing these days. But if we look at the vector space of all continuous real-valued functions on the real numbers, so that's certainly a vector space. It's studied widely, obviously, in calculus, although not necessarily in the context of vector spaces there. But certainly, if we take, continuous real-valued functions on the real numbers, or even let's just take them on the interval 0, 1. So C here is the vector space whose elements are continuous functions whose domain is the interval 0, 1, and whose target is the set of all real numbers. So think of them as functions like which have a graph on the interval, closed interval from 0 to 1, and whose graph there is a single piece. It's a continuous function. Okay, that's a vector space. We've talked about it a little bit in this course, but not that much. Why is it a vector space? Well, if we add together 2 continuous functions, we certainly still have a continuous function as the outcome. And if we multiply a continuous function by a scalar, so if your function is called f and your scalar is 3, then 3f is the function that takes every element x to 3 times f of x. So the vector space structure on this set is sort of fairly reasonable. And it is a vector space that's certainly of interest to many people. It's infinite dimensional, so it wasn't really like the best example for us in terms of defining things like the concepts of bases and finite spanning sets and finite linearly independent sets and so on. But it is certainly a vector space and one that is of great interest. So the assertion is that the analog of the ordinary scalar product on this space is this thing. So if we have a pair of functions f and g are elements of the vector space C. So they are functions defined on the domain 0 to 1 and sending every element of that domain to some real number with the property that they are continuous. Okay, so what this scalar product does is it takes a pair of functions f and g and associates to that pair this number, the integral of the product f of x g of x from 0 to 1 over x. Okay, so it's not obvious at all maybe why this is an analog of the ordinary scalar product or why I would try to sell that idea to you. So let me try to explain why. So if we take an element of Rn, like R3 or R4, then we're basically talking about, essentially a list of 3 or 4 real numbers, whatever the dimension is. If it's an element of R6, then it has 6 real numbers in it. And if you take 2 elements of R6 and take their ordinary scalar product, then you're taking their first entry, adding them together, their second entries, adding them together, their third entries, adding them together, and their fourth entries, adding them together, and adding together all those products of 2 things. So it's a sort of finite process in the sense of the number of operations involved. If we imagine, instead of an element of R4 or R6 or whatever, a continuous function, which is defined in the interval 0 to 1, and actually it doesn't even really have to be continuous for this. We need some sort of some kind of integrable property for this product to be defined. But let's take a continuous function on the interval 0 to 1. Okay, so it's not a list of numbers because the interval 0 to 1 is a continuum. It's not a discrete set of points like 1, 2, 3, 4, 5, 6 when we're talking about elements of R6. But what we have with our continuous function defined in that interval is for every point in the interval 0, 1, we have the value of the function at that point, and that's a real number. So it's not a list of real numbers, but it's a collection of real numbers, one for every point in the interval 0, 1. Because this is a huge set. It's an uncountable set, as we know from last year, but it is a kind of collection of real numbers, one for every number in the interval 0, 1. Okay, and in that sense, like an element of R6 is a collection of real numbers, one for every entry in a vector with 6 positions in it. So there's only 6 of them, so it's quite different in that sense, but it is, in another sense, kind of analogous that we have a bunch of real numbers indexed by something. In the case of a function at the interval 0 to 1, it's indexed by all the elements of this interval 0 to 1, which is a different thing from the list of numbers from 1 to 6, but nevertheless, there's something there that is somewhat similar. Okay, so if you were to take this view and try to define kind of the ordinary scalar product of two functions defined on 0, 1. Okay, so for the two functions f and g, you have a value of f and a value at g on every point in the interval 0 to 1. So if you were to take the values at 0, add them together, take the values at every point in the interval of these two functions, multiply them together. Okay, then you can do this, sort of, at least you can kind of envisage doing it. Okay, take all the points in the interval 0 to 1, take, for each of them, the value of f and the value of g, those are two real numbers, multiply them together. You can't add them together, which would be the analogous thing to taking the ordinary scalar product, because they're defined on a continuum. They're not a discrete collection of things. But you can integrate, and that's sort of the analog of addition when we're working over a continuum instead of over a finite or discrete set. So in some sense, this f of x, g of x is kind of analogous to the a1b1 plus a2b2 plus a3b3 of the ordinary scalar product, and the sum becomes an integral because we're working over this whole interval 0 to 1. So there is some kind of, I suppose, rationale for comparing this definition to that of the ordinary scalar product on the complex numbers. And certainly people work with this inner product all the time, and they work with concepts of orthogonality that are related to it. And one of the prominent examples of that is when people work with Fourier series, which are obviously a hugely important tool in working with continuous functions. And people who work in numerical analysis and differential equations and any form of modeling work quite a lot with this inner product. So you'll certainly meet it again if you continue to work in those areas. Okay, a third example, we're not really going to work with this one, but just to mention that it's out there and that it's something that's useful. So if we take the space of m by n matrices over the real numbers, that's a vector space. It's a very nice vector space that people like to study. And I suppose you could ask yourself, well, what kind of, if you wanted to define an inner product on this set, what might you define it to be? And so that would have to take a pair of matrices m by n and associate to that pair somehow a real number subject to all the required properties of an inner product. So there are numerous inner products defined on this space, but one of them, the most kind of useful, or not most useful, but one of the useful ones that people use a lot, is the so-called Frobenius inner product, or also known as the trace inner product. And the way it's defined is if we take a pair of m by n matrices, A and B, bearing in mind that m and n might not be equal to each other, so the product AB might not be defined, but the product A transpose B always is, because that's a n by m by a m by n matrix. So it's an n by n, it's a square matrix. And we can take its trace, which is the sum of its entries along the main diagonal. So, okay, this looks like a fairly arbitrary definition to make up. But one thing that we can notice if we work with a few examples, just try this out with a 2x3 example if you're curious about it, is that, in fact, the trace of the product A transpose B is nothing but the product of, over the two matrices A and B, sorry, it's nothing but the sum of the products of the entries in corresponding positions of A and B. So if we take the entry in the top left of A and B, multiply them together, add the entries in the 1, 2 position, and so on, work through all the entries of the matrix, then in fact this is exactly what we get, the trace of the product A transpose B. It's the sum over all positions ij in an m by n matrix of the product of the entries of A and of B in that position. So in that sense, actually, it resembles very closely also the ordinary scalar product. An m by n matrix is not exactly the same thing as a vector with mn entries, but it's very close. It's just that they're arranged into an array instead of just into a column. So if you were to sort of take the mn entries and put them into this big long column with the entries from the first row first, then the second row, and so on, then this scalar, this inner product of the two of them would be exactly the ordinary scalar product of those two long columns. Okay, so those are three examples of an inner product. What we're going to do is if we're going to work with any of these in particular, it's just going to be the ordinary scalar product on Rn. We should bear in mind that it's not the only one, and that indeed on a single vector space you may have many different inner products defined. And if there's a risk of ambiguity, you have to kind of be very clear about what one you're dealing with. But I suppose these are some of the I suppose most prominent examples that you see as you go about your business in mathematics. But we're going to sort of, basically our goal is going to be to develop some sort of geometric properties or geometric machinery that a vector space can be equipped with by means of an inner product, once we have an inner product defined on it. So I'm not saying necessarily that everything we're going to talk about has an exact sort of geometric physical realization in the vector space in question, but we can envisage it in terms of what we know about the ordinary scalar product and the notions of orthogonality and distance and so on. So that's where we're headed. So with that in mind, suppose we have a real vector space and that it is equipped with an inner product. Okay, so try not to kind of think only about the ordinary scalar product, but definitely do take that as the sort of go-to example of what's going on. So given any old inner product to find on our real vector space, so it could be the one with the integral, our vector space could be the set of continuous functions on 0, 1 with that integral defined as the inner product. It could be a space of matrices. Okay, so we're going to define the length, or also called the norm, of any element of our space by defining it to be the square root of the inner product of the vector with itself. Okay, and that's it's denoted with by v, the name of the element, with these two vertical bars on each side of it. Okay, so that's a definition that's consistent with the definition of length in Euclidean space. And of course, in Euclidean space, we can sort of justify it by appealing to the theorem of Pythagoras, which tells us that indeed this is the length of the line segment that we have in mind. In general, like for something like a continuous function on a particular interval, we mightn't really have the notion of it being associated to a line segment that has a length, but we can use this definition with that inner product to define something that we're going to call its length or its norm. Okay, and of course we can observe, because of the third property, the positivity property of the inner product, if v is a non-zero vector, then its inner product with itself is a positive real number. So this square root exists and is a positive real number. If v is the zero vector, then its inner product with itself would be 0, and this number would be 0. But in all other cases, it will be a positive number. Okay, once we've got that idea of the length of a vector, we can define the distance, the notion of distance between two vectors u and v, to simply be the length of their difference. If u and v are vectors in a vector space, we can subtract one from the other, and we can define the distance between them to be the length of their difference. Okay, and the third thing that we'll say is, again, by consistency with the scalar product in Rn, that a pair of vectors u and v are orthogonal with respect to the inner product that's defined in the space that they live in, if their inner product with each other is equal to 0. Okay, and the assertion is these definitions are consistent with the sort of typical geometrically motivated concepts of distance and orthogonality that we see in the context of the ordinary scalar product on Euclidean spaces. And so this sort of enables us to kind of carry over at least some algebraic interpretations of these geometric notions into more general vector spaces, which turns out to be quite a powerful idea. Okay, a couple of further remarks about the length or distance function in particular. So an element of a vector space is referred to as a unit vector if its length is 1. And of course, for that, you have to have an inner product defined on your vector space so that you have a concept of length defined on your vector space. Okay, and the length of elements, or the norm of elements, has the property that if you take a vector and multiply it by a scalar, so see here is some real scalar. There's a z here, which shouldn't be there. Apologies for that, it's a typo. But the length or the norm of the scalar multiple cv of v is just the norm of v multiplied by the absolute value of the scalar c. And again, this is something that's familiar to us from the ordinary inner product, or even just from ordinary vectors in Euclidean space. If you take a vector in R2, multiply it by 2, okay, you've doubled its length and preserved its direction. If you take a vector in R2 and multiply it by -2, you've reversed its direction, but you've doubled its length. So multiplying by a scalar scales the length of the vector by the absolute value of the scalar that you multiplied by in a real vector space. And that's true for any length function defined by any inner product, not only for the ordinary Euclidean length function. So I suppose this is maybe the reason or a reason why the term scalar is used, that the effect of multiplying a vector by a number is to scale its length. Okay, and of course, if you want to kind of confirm that this is true, just look at the definition of the length of a vector and apply it to a scalar multiple of some vector v. If we're in an inner product space, the length of the scalar multiple cv of v should be the square root of the inner product of cv with itself. That, by the bilinearity property, is just the inner product of v with itself multiplied by the scalar c squared. And the positive square root of c squared is the absolute value of c. There should be an absolute value sign here. So that's this equation applies exactly as written if c is a positive scalar. Okay, so we can adjust the norm of any element of v while preserving its direction if we multiply it by a positive scalar. And so in particular then, if we have any old non-zero vector in an inner product space, and we'd like to have a vector of length 1 in the same direction as this one, we can just adjust the vector that we have by multiplying it by 1 over its own length, and that will scale its length back to 1. Okay, so this vector is a unit vector in the direction of v, often denoted by v with a little hat on top, and it is referred to as the normalization of v in some context at least. So it's a useful kind of thing to have in your toolkit to be able to scale a vector to adjust its length to be 1 if there's reason to do that, which sometimes there can be. Okay, the last thing I want to mention in this lecture is the concept of orthogonal projection. Okay, so here again, we will take the example of R2 and the ordinary Euclidean product as a starting point. Okay, so before heading into the sort of abstract terms, let us recall what we mean by orthogonal projection in R2. So the setup here is we have a pair of non-zero vectors u and v. In R2, we'll assume that they point in different directions, so that they're not scalar multiples of each other. And the idea of the orthogonal projection of v on u is that we can imagine the one-dimensional subspace spanned by u, which I'm going to indicate here in this red color. Okay, so it consists of all scalar multiples of u. We can imagine the origin in the Cartesian plane to be here at the shared initial point of both v and u. Okay, so the idea is that we can represent v, no matter what v is, as the sum of a vector that has the same direction as u and a vector that's orthogonal to u. So here, by orthogonal, we can think of perpendicular, the usual sort of geometric meaning of orthogonal in Euclidean spaces. So if we draw a line through the endpoint of v that's perpendicular to the line through u, so that's the one-dimensional subspace spanned by u, so it ends up here somewhere, then we can rewrite v as the sum of this vector, which runs parallel to u, which is a little bit longer than u in this particular example. It could be longer or shorter in general. So this red vector is a scalar multiple of u, which I'm just going to write as au, and this other red vector, which is perpendicular to that, I'm going to call it v dash, and it is orthogonal to u. So v can be written as a scalar multiple of u plus a vector v dash, which is orthogonal to u, so au is a scalar multiple of u. Obviously, I'm just writing this for emphasis. It's already been said. The point is that au is an element of the one-dimensional subspace spanned by u, and u and v dash are orthogonal to each other. So we can always break a vector v up into a component that's parallel to any prescribed given direction, plus a component that's orthogonal to that direction. And the vector au is the orthogonal projection orthogonal because the other part of it, the complementary part of v, is orthogonal to u. It's the orthogonal projection of v onto u, or more correctly really, but also more long-windedly, onto the one-dimensional subspace spanned by u. And then v is the sum of this vector, which is perpendicular to u, plus this other vector v dash, which is orthogonal to u. Okay, so with this picture, I mean, the justification for the assertion that this can always be done is kind of geometric. We're just saying, look at the picture. Okay, well, here's how you do it. You just sort of take the, take the vector in the direction of u, whose endpoint would make a line segment with the endpoint of v that's orthogonal to u, or take the line through the endpoint of v that's orthogonal or perpendicular to the line through u. And that certainly works in this setup where we have a fairly concrete geometric structure. One might, of course, ask, if you had a pair of vectors u and v in R2 like this, and they were given to you in the form of coordinates, how would you actually find this number a? So a question that we might ask is how to find a, and that's something that we can answer using the machinery of the ordinary scalar product and of inner products in general. So let's go back and see how we can do that. Okay, so in general, our setup is that we have a pair of vectors in an inner product space. So the inner product in the case of R2 is the ordinary scalar product. Okay, so we're thinking about v. We've got this. So think about u as sort of defining a specific one-dimensional subspace of v, like a line through the origin in R2. Okay, we've got some vector v, any old vector v, and we want to write v as the sum of a vector in the direction of u, or the opposite direction. So a vector, a scalar multiple of u, plus something that's orthogonal to u. Okay, and the assertion is we can always do that, and that we can figure out indeed how to do it and how to use the inner product to do it. By orthogonal here, we mean orthogonal with respect to this inner product, that the inner product of v dash with u should be 0. Okay, in the case of the scalar product, that means the ordinary scalar product of u dash of v dash with u should be 0. Okay, so here's how we do it. So if v is already orthogonal to u, which is a sort of special case, then just take v dash to be v and take a to be 0. That means that v is already orthogonal to u, so fine, that's already done. The other case that's already done is if v is already a scalar multiple of u. In that case, v is just some scalar multiple of u and v dash is 0. But the other more generic and more typical case is the case where v and u point in genuinely different and non-orthogonal directions. So what we want is to have an equation satisfied that says v is equal to au plus v dash, where v dash is orthogonal to u. Okay, and what we'd like to do is we'd like to know, for a particular example, how to find the a that does this trick. So in order to solve this equation for a, something that we can do is take the inner product on both sides with u and use the fact that the inner product of u with v dash should be equal to 0. So taking inner products on both sides with u, we get uv on the left equal to inner product uu multiplied by the scalar a on the right plus inner product of u with v dash, which we want to be 0. So that's achieved if we solving for a, we take a to be the inner product uv divided by the inner product uu, which is, if you prefer to write it this way as the length of u squared, you can. If you prefer to write it as inner product of u with u, that's completely fine as well. Okay, so the conclusion then is that v is u multiplied by this particular scalar, u dot v divided by u dot u. Okay, and then the v dash part, okay, is just the difference between, is just the difference v minus this part. Okay, but we can certainly verify directly that the two components in this expression are orthogonal to each other. And if we want to figure this out for a particular example, we can certainly do so. So let's have a quick look at this particular example, where u is 2, 1, and v is 6 minus 2 in R2. So in that case, to compute the orthogonal projection of v on u, which is this vector u dot v divided by u dot u times u, we can proceed in the following way. Okay, so our goal is to calculate the au and the v dash for which u is orthogonal to v dash. Here are u and v. And the instructions on the formula that we just developed in the previous slide says that a should be the scalar product u with v divided by the scalar product of u with u. So in the example here, u dot v is 2 times 6 plus 1 times minus 2. So it is 10, 12 minus 2. U dot u is 2 squared plus 1 squared. So it is 5. So a should be 2 then. 10 over 5 is 2. And we should find that au is 2 times 2, 1, which is 2 times 2, 1, which is 4, 2. And v dash should be v minus au. V was 6, 2, 6 minus 2. Au was 4, 2. So this difference is 6 minus 4, which is 2, minus 2 minus 2, which is minus 4. And we can confirm immediately that v dash is indeed orthogonal to the u that we started with. So au here, 4, 2, this is the orthogonal projection of v on u for this particular example in R2. Okay, so in general then, for a pair of vectors u and v in an inner product space v, the scalar multiple of u, which is given by multiplying u by this quantity, inner product of u with v divided by inner product of u with itself, this is called the projection or the orthogonal projection of v on the one-dimensional space spanned by u, or if you want to write it in a kind of shorthand way, you can just call it the orthogonal projection of v on u, but really we mean in the direction of u, not really on the vector u itself necessarily, in the sense that if we replaced u by a different element of the same one-dimensional space, this orthogonal projection wouldn't change. Okay, so it's denoted by projection of v on u like this, projection of v in the brackets here on u, u is written as a subscript is the one we're projecting onto. And the property that it has is that the difference v minus this projection, this part of it that's projected onto u, is orthogonal to u. So another way to say it, v is the sum of this projection on u plus another part, and the other part is orthogonal to u. Okay, so another characterizing property of the projection of v on the one-dimensional subspace spanned by u is that this vector, the projection of v on u, this particular scalar multiple of u, it's the unique element of the one-dimensional space spanned by u whose distance from the vector v in the sense of the distance function defined by the inner product is minimal. Okay, so to see that, let's look at the distance from the vector v to any scalar multiple of u. And of course, in the case of the example from R2, basically the vector AU, it was the nearest point on the line through u to the endpoint of the vector v, which is exactly what we're saying here. Okay, so to see why this is true in general, let's give ourselves a scalar multiple AU of u. So this is any element of that one-dimensional space spanned by u, and look at the distance from v to AU. Okay, so we're basically wondering what point, for what value of a is this distance minimal. Okay, so the square of that distance, which is easier to write down because it's just the inner product of AU minus v with itself, is if we expand out the brackets here using the bilinearity property, this is a squared, u inner product with itself. We've got minus AU inner product with v, minus AU inner product with v, that's there twice, so minus 2 times a inner product of u with v, plus the inner product of v with itself. And here we're using the symmetry property to write v comma u and u comma v, both in the form u v. So this expression, so remember everything here is a real number. These inner products of vectors with each other are real numbers, and a is a real number. So we can, we're thinking about the distance between v and scalar multiples of u. They're parameterized by the scalar multiple a, which is a real number. So we can look at this expression as being a quadratic function of a. And for a fixed pair of vectors u and v, the three coefficients here, uu, uv, and vv are all fixed. So to calculate its extreme values, we can just take its derivative and look at where it's minimal. So if we regard this as a quadratic function of a, it has a minimum when its derivative is 0, which will be saying that 2a times the inner product uu minus 2 times the inner product uv is equal to 0, which is exactly saying that a has the value that we had already identified, which determines the orthogonal projection of v on u. We'll see a more general version of this argument in the next lecture. Okay, that's it for now. What we're going to do next is extend this idea of orthogonal projection to the orthogonal projection of a vector onto a subspace, which does not necessarily have dimension 1. Okay, so see you next time for one last installment. Thank you, everybody.